Okay, students, really happy to meet you again. In this particular class, we are going to discuss very important theorem in the algebra. Okay, what is the theorem? The first counting principle in that particular topic. The first theorem is very important theorem. Okay, we will discuss that now. Okay, right now let us take the screen. Now this is the first theorem in counting principle. Okay, in the counting principle, this is the first theorem. Okay, now what the theorem says, hk is a subgroup of G, implies hk equals kh. Okay, hk is a subgroup of G if and only if the left coset should be equal to the right coset with h and k. That's what we have to prove. Okay, so let us prove that now. Oh, let us prove that now. So we will close this particular board. Let me erase that. Okay, let me erase that. And afterwards we will prove that particular theorem, fully understand everything, and afterwards we will be proving that. Okay, what actually went on here? Here also we have to, and we have to clear this also. Okay, so happy that you are here. We will prove that particular theorem now. Okay, now what is the theorem size? Hk is a subgroup of G if hk equals kh. That's what our aim to prove here. Okay, so here you understand G is a group. So what I am doing here, now suppose that G is a group. This is a group I am taking. Okay, right now suppose kh is this particular subgroup, and another one I am taking as kh is other subgroup. You suppose kh is another subgroup. Now what we have to prove, that both of them are equal. Hk, right coset, should be equal to left coset. That's what we have to prove here. Okay, that's a fundamental that we have to prove here. So how can we prove that? Okay, right now what I'm going to do now, to prove, we know already that, am I correct, to prove a set is contained in another set. Suppose A is a one set, B is another set. To prove that, what we used to do is that we will, to prove that they are equal, first we have to prove that A is contained in B and then B is contained in A. That's what we usually used to do. Am I correct? That's what we do. The same thing we are proving here. So to prove this, what we take, one element we take belongs to this, then that element belongs to this, therefore this is contained in this. Then afterwards we'll take one element in this set, then afterwards we prove that that same element belongs to A. That's the way we are used to prove. Am I correct? So in the same way we are going to prove that I'm going to take one element in the xk set, and I am going to prove that the same element belongs to kh also. Then afterwards I will take one element in the kh, then I used to show that the same element belongs to hk also. That is what. So only tool that we can use here is hk is the subgroup of G. That's what only the tool we can use there. Hk is a subgroup of G. Only that tools, by using that tools we have to prove that. This is what I'm going to do now. So let me take one element. I am taking one element h. Suppose h is an element. Suppose h is an element belongs to this particular set HK, where one element from H and another one element from K, which implies if H belongs to HK, definitely X inverse also belongs to HK, because G is a graph and H inverse should belongs to HK, capital HK. Right. Now this implies what? Definitely X inverse belongs to HK implies X inverse would be of the form one element from H, the another element in the K. That order it would be. Am I correct? Therefore, we can say that HK inverse, HK inverse, and definitely that belongs to HK. But from the subgroup definitions or from the lemma, we know that this HK inverse is exactly equal to K inverse H. K inverse into H inverse. But K inverse H inverse belongs to which set? K is first, H is second. Am I correct? So it will belongs to K into H. K into H. So what we have proved, X belongs to HK implies that can be written like this, that can be written like this, that can be written like this, and that belongs to KH. That means X belongs to KH. So what we understand by now, we proved that HK is contained in KH. Now next what I'm going to do is that I'm going to take one element here, Y belongs to KH, okay, right. Now Y belongs to KH implies Y inverse also belongs to KH. But Y inverse is what? Any element of the type KH. Am I correct? So this I can write it as K into H inverse. K into H inverse. That is of the form K into H inverse. But this from subgroup, we can write this as H inverse into K. H inverse into K. H inverse. What we have to get here is that H inverse into K inverse. Am I correct? H inverse into K inverse. But H inverse into K inverse, they see the form of them. This is a right coset like. We will get that this is definitely this belongs to which set? HK. So what we understand here, if Y belongs to KH, then Y belongs to HK. That's what we understand. Am I correct? Y belongs to KH implies Y belongs to HK. That's what we have proved. Am I correct? So what we understand that if X belongs to HK, then X belongs to KH, that means HK is contained in KH, and if Y belongs to KH, Y belongs to HK, which implies KH is contained in HK. Therefore, both of them gives some idea that both are equal. HK equals KH. So that's a way we can prove our theorem here. Okay, so this is a way we can prove our theorem. So thank you very much.